Good afternoon, classmates. Good afternoon, Sir Mercado. We are the Group 5. Yours truly, Sandilyn Collado, Sir Marlo Robles, Ma'am Carmen Jane De Pedro, and Ma'am Mary Joyce Pangilinan. Today, me and Ma'am Carmen Jane De Pedro will present to you the related research that we have with our topic, which is motion through MU. The research entitled An Experimental Verification of Newton's Second Law. The researchers were Roberto Hessel, Saulo Ricardo Canola, and Dimas Roberto Voleta. And this was published April 24, 2000. The researcher's introduction. To introduce Newton's second law or concepts such as force, inertial, and gravitational mass and weight, it is a common practice to use the approach offered by PSSC Physics that, according to Aarons, is quite reasonable for introductory levels. In the PSSC context, Newton's second law of motion is investigated in the laboratory, with guards, times, and a rubber loop stretch a constant amount as the unit of force. The choice of stretch elastics to accelerate a cart on a level table is quite suitable as the starting point because it takes into account the intuitive notion of force related to a sensation of muscular effort, but due to the difficulty of keeping the rubber loop stretch a constant amount as the cart accelerates, the quantitative results are not always convincing. Indeed, only the more attentive pupils obtain satisfactory results. For this reason, when they follow the sequence outlined in PSSC, they complement the laboratory activity with an experimental demonstration that allows confirmation of the validity of Newton's second law in a quick and convincing way. So they had experimental setup. The experimental setup consists of a glider on an air track connected by a string passing over a small pulley to a hanging load of mass m and weight mg. They consider the glider and the load as a single object, subject to the accelerating force. To show that the acceleration of the system is proportional to the acceleration force when the total mass is kept constant, they begin with a hanging load of mass m and add 4 identical metallic discs of mass m to the glider of mass m. So here in figure 1 shows a simplified drawing of air track showing the hanging load and the glider loaded with metallic discs. Therefore, the accelerating force mg acts on a system total mass m plus 5m. To double the accelerating force, one disc is transferred from the glider to the hanging load. To triple the force, 2 discs are transferred from the glider to the hanging load, and so on. To show that the acceleration of the system is inversely proportional to its mass when the accelerating force is kept constant, we change the mass of the system by loading the glider, or they change the mass of the system by loading the glider with mass of the different sizes or connecting another glider to the original. The acceleration can be determined from the average speeds calculated for successive time intervals of the motion. They have measured time intervals by using electronic counters in conjunction with a single crystal oscillator circuit operating at 1 kHz and a photogate. So here, the figure 1, this is now the timing circuit. The counters have 2 inputs, the clock CK and the clock enable CLEN. The first receives rectangular pulses sent by the oscillator and the other enables the counting process, when it is held at ground state. When the logic state at this input is high, the counting stops. The heart of the circuit is the 4017. The 4017 is a decade counter with 10 outputs that go to high in sequence when a source of pulses is connected to the clock input and when suitable logic levels are applied to the reset and enable inputs. So briefly, the electronic circuit works as follows. If the logic state at the S sub 0 output is initially high, the S sub 1, S sub 2, until S sub 5 outputs are low, and the state at each CLEN input is high here due to the presence of the NOT gate. Consequently, all counters are blocked because an H level or high level of the CLEN input inhibits the clock operation. When the clock's input of the 4017 receives the first impulse, the high state is transferred from S sub 0 to S sub 1. And the first counter starts the timing. When the second pulse arrives, the state at S sub 1 changes from high to low, and the S sub 2 goes to high. Then the first counter stops the timing, and the second starts. Finally, when the sixth pulse arrives, S sub 5 goes from high to low, and the fifth counter stops the timing, while S sub 0 goes to high again, because the S sub 6 output is connected directly to input reset. The pulses that arrive at the clock's input of the 4017 are generated during the passage of pulse transported by the grinder through a photo gate. The grinder, 6 posts evenly spaced on a wooden ruler fixed to it, as you can see here in figure 3. This is now the simplified drawing of the grinder carrying 6 evenly spaced posts. So, after the posts have passed through the photo gate, the counters record in MS. The time intervals, we have T1, T2, until T5, indicated here in figure 3. If the distance between successive posts is D, the average speed of the grinder in the time interval, T sub 1 is average velocity sub 1 is equal now to D over T sub 1. In T sub 2 is average velocity sub 2 is equal now to D over T sub 2, and so on. The set of these values may provide information regarding the motion of the grinder. And their analysis of the data. The researchers' analysis of the data. They consider the expression average velocity is equal to 1 over change of time of the definite integral of v dt from t sub 2 to t sub 1, where change of time is equal to t sub 2 minus t sub 1. Expanding the integrand into Taylor series about t is equal to average of time about the midpoint of the interval, they obtain an experimental verification on Newton's second law. The first equation is average velocity is equal to 1 over change of time of the definite integral of v times average of time plus first derivative with respect to time times t minus average of time plus 1/2 factorial of the second derivative with respect to time times the squared of t minus average of time plus from average of time plus change of time over 2 to average of time minus change of time over 2, where this is equal to first derivative of v with respect to t, and a, this a that above is equal to the second derivative of v with respect to t, and so on. Setting the constant time is equal to t minus average of time and integrating the series by the term, the first equation can be written as average of velocity is equal to v times average of time plus first derivative with respect to time over change of time times squared of the constant time over 2, that is from change of time over 2 to negative change of time over 2 plus 1/2 of the first derivative with respect to time over change of time times the cube of constant time over 3 from and change of time over 2 to negative change of time over 2 plus . This is now the equation 2. The terms in constant time squared, constant time cube, and so on are all 0, so that the equation 2 reduces to average velocity is equal to velocity or v times average of time plus 1/2 the second derivative with respect to time times the squared of change of time over 12 plus 1/2 of the third derivative with respect to time times change of time raised to 4 over 80 plus . This is now the equation 3. By inspection of equation 3, they concluded immediately that for constant acceleration a, average velocity is equal to v times average of time. But the converse is also true if for any change of time, average velocity is equal to v times average of time. This condition is fulfilled if second derivative with respect to time is equal to the third derivative with respect to time, which only happens when a is constant. So to analyze the motion of the glider, they assume the initial that velocity times average of time is equal to average of time for any change of time. If this is true, then the graph of velocity times change of time versus t is linear, and the slope of the straight line is the acceleration of the glider. And the acceleration can also be obtained by analyzing the distance traveled by the glider as the function of the time. The continuation of this research, the applications, and the conclusions will be presented by Ma'am Charmaine Jane De Pedro.
Good afternoon, classmates, and good afternoon, Sir Mercado. I am Charmaine Jane L. De Pedro, one of the presenter of the research that we have in group number 5 about motion through a medium. So, my part is about the application. Relation between the acceleration and accelerating force for constant total mass. The glider shown in figure number 3 was loaded with a 4 metallic discs having a mass of 50 grams each and was connected to a hanging load also weighing 50 grams by a string passing over a small pulley. The system glider plus the hanging load with a mass of 1,502 grams was then released. At the end of the run, the counters recorded the time intervals represented by T sub 1, T sub 2, T sub 5. Afterwards, one of the discs transported by the glider was transferred to the hanging load, and the procedure above was repeated. We carried out the same thing with the remaining discs. The time intervals recorded on the counters after each run are shown in the table number 1. So this is the table number 1. So as you can see on the left side, hanging load, gram. So there is 50, 100, 150, 200, and 250. On the right side, there is the change in time. Okay, so this is the time interval. So T sub 1, T sub 2, T sub 3, T sub 4, and T sub 5. Knowing that the distance between the two consecutive posts is 12 cm, we can determine the average speed of the glider at each time interval. For instance, table number 2 shows that the average speed calculated for the first run. So this is the table. Figure number 4, speed versus time curves for a system glider subject to a constant force. The dashed line refers to the average speed, whereas the solid line refers to the instantaneous speed at the midpoint of each time interval. So, linear figure, so V is equals to 23.28 plus 30.99 times 10 raised to the negative 3 t with t in meter per second. Figure number 5, acceleration of the system, glider plus hanging load as a function of the hanging load for a system of constant mass. Linear figure A is equal to negative 1.594 plus 0.643 m sub ht. So this is the figure. Conclusion. Based on the research, they said that we have described a way of showing effectively and quickly the proportionality between acceleration and force of a fixed mass and between acceleration and inverse of mass for a fixed force, as predicted by Newton's second law. In addition, the technique that we have used to determine the acceleration of the moving objects affords a good opportunity to discuss certain questions concerning the average speed, instantaneous speed, which have little chance of being treated in laboratory classes. The experiments proposed are easy to perform and are appropriate for both undergraduate laboratories and demonstration in class lecture, since the students have already acquired some level of familiarity with the basic concepts such as mass and weight. These are the reference of the research that we have. That's all about our research about motion through a medium. So we are group number 5, stay home, save lives. Thank you.